Okay, so what we have here is this very cool visualization of global wind patterns. So here is this movable globe here, kind of just like Google Earth. And if we zoom in a little bit here on the Pacific Ocean, here's the equator. We'll start to see these really cool lines, right, showing us the global wind patterns in the Pacific Ocean specifically. And so what we notice is this very strong trend of the winds moving sort of to the southwest, kind of towards the equator like this. And then in the southern part of the Pacific Ocean, we see this really strong wind moving towards the northwest, right? So sort of diagonally moving towards each other from about 20 or 30 degrees north and south towards the equator. We see that very same thing if we come over here into the Atlantic. Here we go. See this very same thing where we have these very strong sort of southwest directed winds in the northern hemisphere, and then these very strong sort of northwest directed winds in the southern hemisphere, right? And so that's a very cool pattern, and we're going to sort of explore the reasons for that pattern. Okay, so we can understand where those cool global air circulation patterns come from simply by remembering this idea that everybody's familiar with, and that's that hot air rises. So if hot air rises, then of course it stands to reason that the equator is going to have the hottest air because the equator receives so much direct sunlight, right? So we know that the equator is hotter than the poles. So over here on the left, we've got this little cartoon of the Earth. We've got the equator here, 0 degrees latitude. Dashed lines are 30 degrees north, 60 degrees north, and then 30 and 60 degrees south. And then, of course, we get the North and the South Pole down here at 90 degrees north and south, respectively. So intense heat from direct sunlight at the equator causes lots of evaporation of ocean water. So then that evaporation, combined with the fact that it's hot, makes hot, wet air rise at the equator. Okay, so direct sunlight causes evaporation, and then that hot, wet air from all that evaporated water rises high into the atmosphere. As it does that, it cools off, and when hot, wet air cools off, it condenses and causes rain, right? So another word for rain is condensation, because as that water cools off, the water vapor condenses and forms water droplets that then fall back down to the earth. Okay, so that evaporation and then rising and sort of condensation of water making rain fall right back down on the equator is why the equator is so wet. It's why it's so rainy in the tropics because there's so much evaporation and then most of that water just falls right back down where it came from. So once that air rises sort of high enough in the atmosphere, it actually is going to start to head towards cooler areas, right? So it's a sort of a consequence of the second law of thermodynamics that hot things move towards cold things. So that hot air, as it rises, it's going to move to the north and to the south, right? Because we know that both the north and the south are cooler than the equator because they get less direct sunlight and light's more likely to reflect off of them, like we talked about in the last video. Okay, so that air moves north and moves south, it cools even further, and it rains even more. So what that means is by the time that that air gets to about 30 degrees north or about 30 degrees south, it's very, very dry, and it's starting to cool off quite a lot. So if hot air rises, then cool air sinks. So that cold, dry air sinks back down to the earth. So the fact that this air is cold and dry is actually very important for sort of understanding the global distribution of deserts. So it sort of turns out that most of the world's sort of deserts are in this arid belt that occurs at about 30 degrees north and south of the equator. So I have these arid belts. These arid belts with most of the world's deserts form because of this cold, dry air sinking back down. And so if you picture the globe, and I'll show this in the next clip, if you picture the globe, the Sahara, the biggest desert in the world, is in North Africa, about 30 degrees north of the equator. The desert southwest of the United States is sort of also at a similar latitude. And in the south, we've got parts of South America that are very desertish, and Australia is also well known for being a desert and sort of at about this latitude. So a lot of the driest parts of the world are at this 30 degrees north and south area because of this cold, dry air sinking back down to the surface of the earth. Okay, so because this air is sinking back down to the surface of the earth, it's actually creating an area of high pressure at the surface of the earth. We have high pressure at the surface of the earth. We have this high pressure atmosphere at 30 degrees north and south because of the sinking air sort of pushing, exerting pressure down on the surface of the earth. And then similarly, right at the equator, where the hot air is rising, that's an area of low pressure, right? So we have low pressure here at the equator and high pressure belts at 30 degrees north and south. This causes the air to flow back towards the equator along the surface of the earth, creating these winds that are moving from about 30 degrees to the south and to the north towards the equator. Okay, so that's sort of the cross-sectional view, but something very interesting happens in sort of plan view or map view as we're looking down on the surface of the earth. Okay, so we know that the earth is spinning, right? So if this is north up here, south, we've got east and west over here. We know that the sun rises in the east and sets in the west, right? So if you think about standing stationary on a surface, moving towards the sunrise, we must be rotating in this direction. Okay. But the Earth is rotating around its axis right here, right? So if you imagine looking sort of top down on the globe, okay, so here's the North Pole, and then this would be the equator. Just pretend that's a little bit rounder than it is. Or you can imagine like a ceiling fan or one of those really awesome, wind turbines we have out here in Amarillo, right? The tips of the fan must be moving faster than right near the sort of center of the fan, right? The tips have to be moving faster than the center. So that means that the equator is rotating much faster than the rest of the world. So it turns out that the equator is rotating at about 1,670 kilometers per hour, right? Really, actually pretty fast. And then at about 30 degrees north, it's rotating slower at about 1,450 kilometers per hour. So this difference in the speed of the rotation of the equator versus other places north and south gives rise to this thing called the Coriolis effect. Oops, the Coriolis effect, that should be an I. Coriolis effect. And so basically what the Coriolis effect does is it ends up causing this predictable deflection in the flight path of things like airplanes or moving masses of air. So you can imagine, flying from, let me draw like a little map here. So we've got Texas Panhandle. Here's Big Bend. Okay, here's a pretty crummy Texas. Oklahoma, Kansas, Nebraska, and let's see, okay, so New Mexico is kind of like this, and Colorado. Okay, great, so we're here in Amarillo. You can imagine if you took off in a plane from somewhere up in Nebraska and flew straight south, right, you would sort of expect to arrive in Amarillo. But you gotta remember that Amarillo is rotating faster than Nebraska is, right? So you're actually gonna, because this is moving faster than you are and you preserve your sort of angular momentum, you're gonna maybe end up actually landing in Albuquerque, right? Because this is moving faster underneath you than Nebraska is. So that Coriolis effect sort of causes these moving air masses that are going from high pressure at about 30 degrees north and south to have this deflection in their air path, causing these wind patterns that look like this, just like we saw in that groovy animation. And now this pattern of air circulation, these are called Hadley cells. Named after the person Hadley, who sort of first described them. And they're only one of two other sort of major circulation systems in the global atmospheres. So again, we know that hot air rises and cold air sinks. So at the North and South Pole, where the air is very, very cold, we have sinking air, right? So that causes high pressure at the poles, high pressure, and then that moves towards an area of low pressure at about 60 degrees north and south, low pressure. Okay, so we've got sort of sinking air, moves towards low pressure, sinking air, towards low pressure. And then same thing when we have this sort of between 30 and 60 degrees north and south cycles. We've got area of high pressure, so the air at the surface tends to move towards those low pressure areas, right? Setting up sort of another circulation cell just like this. So you can think of these three cells, the polar cell. These intermediate ones are called Ferrel cells, again, after a person. Ferrel cells. These three different cells, the polar, the Ferrel, and Hadley cells, act as sort of gears, right? Where we've got air going in this view, sort of counterclockwise here, and then clockwise in the Ferrel cell, and then counterclockwise again in the polar cell. So these three different cells all circulating air between about 0 to 30, 30 to 60, and 60 to 90 degrees. And these three circulation cells basically take hot air from the equator and slowly make its way in this sort of winding path up to the poles, or down to the poles, if you will. Right, so it's this global air circulation pattern that's ultimately caused by this uneven distribution of heat from the sun. And it makes these predictable weather patterns. So this is a climatic system, right? This system is operating on a large scale throughout space and time, but small perturbations in this larger process give rise to our daily variations in weather.